This is the start of Chapter 3, Ecosystem Ecology. This chapter is really going to get into some meat of AP environmental science, including looking at food webs, looking at trophic levels, looking at the very important biogeochemical cycles. Those cycles are going to require you to put a little effort to make sure that you learn them. They are a key part of this curriculum. This opening picture is a picture of Haiti, and in 2010 there was a devastating earthquake that happened there. But even before that, Haiti has a lot of poverty, has a lot of issues. 76% of Haitians lived on less than $2 a day, and part of that is oil and propane then become too expensive to use as cooking fuel. And so Haitians turned to using charcoal or using wood to burn to be able to cook things. By 1923, 60% of this country was covered in forest, and by 2006, only 2% of the land remained forested. There's 9 million people there. Most trees in Haiti are cut before they grow to be more than a few centimeters in diameter. And because of this deforestation, it leads to tons and tons of erosion because there's no roots to stabilize the soil. Anytime a tropical storm or hurricane comes through, there's no vegetation to stop that water runoff, and so there's massive mudslides. Things have been getting better. They've been planting 60 million trees there. But one of the things that has really sort of helped is Haitians would often just cut the trees as soon as they could. There is planting mango trees. Mango trees can yield $70 to $150 worth of mangoes annually, which is a huge profit for the Haitian people. So the motivation to let those trees grow is high, and that can help offset the problem of this deforestation. It's just another aspect of what happens in environmental science, where we can sort of look at a problem but then have to look at alternative ways to solve it depending on who the population is that we're dealing with. An ecosystem, which is our first definition here, is a particular location on Earth distinguished by a particular mix of interacting biotic and abiotic components. So biotic is the living components and abiotic are the non-living components. Some ecosystems have very defined boundaries. A cave, we could say this is the cave, and so therefore this is the ecosystem. We could say this is the lake, and this lake defines the ecosystem. But most of them it's very difficult to determine because one ecosystem naturally sort of overlaps into the other ones. Looking at examples of ecosystem, this little drop here, this can be an example of a very small ecosystem. These little unicellular, multicellular, small creatures live in this little teeny drop here. Another ecosystem could be Yellowstone National Park. It was originally sort of thought that, okay, well, the park is an ecosystem. And this, this sort of extends into what, like the national forests. And then actually there's some private land. And so it was sort of determined that this boundary is the boundary of the greater Yellowstone ecosystem. Certainly not a perfect boundary, but the idea that we can impose boundaries and say, well, this is the park, and therefore that is the boundary, and it's not really always true. You have to look at different factors that play into it. If you have not had a chance to visit Yellowstone National Park, you need to put it on your list of places to go. It is absolutely fantastic and phenomenal, along with the Tetons. I'm looking forward to going back in the near future. If we look at what's called ecosystem processes, even though it's helpful to distinguish between two different ecosystems, they interact with each other. And we're going to look at that through energy flow, which is what this is bringing up, this idea of energy flow. And the way we identify energy is through photosynthesis and respiration. So photosynthesis, our producers, which is another word for autotrophs, or autotrophs and producers are synonymous. So those are our plants, are able to use the sun's energy to produce usable energy through photosynthesis. So if we look at our plant leaf here, it takes in energy from the sun, it takes in carbon dioxide, it takes in water, and produces glucose, a sugar, that can be used by heterotrophs, and it produces oxygen. Okay, this is performed what we typically think of as plants. Plants are our big autotrophs, but some algae and some bacteria also fit into this category. Respiration is performed by all organisms, and that's where they're taking in oxygen, taking in these sugars, and giving off energy, giving off carbon dioxide, and giving off water. Okay, so these are our two sort of competing processes that happen. Cellular respiration is the process by which other organisms gain energy from eating the tissues of producers. Okay, so producers are the start of our food chain and the start of our source of food. And then respiration is the process by which those organisms are able to take in what those autotrophs are able to produce. If we start looking at trophic levels, food chains, food webs, this is going to be a key. There's sort of two key parts of this chapter. One is this idea of food chains and food webs. Always shows up on the AP Environmental Science exam in some fashion. Consumers, which are heterotrophs, that's that other vocab word, obtain energy by consuming other organisms. So they need to eat things that have made energy in some other way. Primary consumers are a specific type of consumer, and they consume producers. They're herbivores. They're essentially our vegetarians. So vegetarians are eating at the lowest level of the food chain. They're eating the grasses, the bushes, the shrubs, the berries, those sorts of things. Secondary consumers are carnivores, and they obtain their energy by eating primary consumers. So they are eating the things that have eaten the grass, leaves, berries to get energy. Tertiary consumers are further up the food chain. They are also carnivores, and they eat secondary consumers. So they're eating the consumers that have eaten the primary consumers. So you're working your way up the food chain. And so here's a good example of a couple of different food chains. Okay, looking at this aquatic food chain here, we have algae, which is going to photosynthesize. That's going to be our autotroph. And then we have this little tiny zooplankton, which is eating the algae. Working our way up, we have the fish that's going to eat the zooplankton. That's going to be our secondary consumer. And then the bald eagle is going to eat the fish, which makes it a tertiary consumer. So primary, secondary, and tertiary. We have our producers here, which are the grasses. And then the zebra is a vegetarian, will eat these grasses. And then the lion will come along and he'll eat the zebra. He's a secondary consumer. It never goes above a tertiary consumer. Part of the reason why, and this is a very key idea to food chains and food webs in this unit, is this 10% rule. Only 10% of the energy that's harvested by each level can be passed on to the next level. So if we look at our grasses and we consider them, to be sort of our producers or whatever, only 10% of the energy of these grasses can make it to the zebra. And only 10% of the energy stored in the zebra can make it to the lion. So once we get above tertiary, there isn't enough nutrients, that sort of pass through. There isn't enough energy gain that passes through that allows it to be effective. That 10% rule is a real key idea to keep in mind for the AP science exam. A food chain is the sequence of consumption from producers through tertiary consumers, and this is a food chain. These are chains, grass to zebra to lion. A food web is more realistic. It takes into account the complexity in nature. And so here's a food web, and it's looking at all the different things. So we have these producers, they have indicated with the green dot here, which are the grasses. And then our primary consumers are our vegetarians. So our hare is a vegetarian. Our zebra here is a vegetarian. The wildebeest here, poor dead wildebeest, is a vegetarian. And then we move on to our secondary consumers, which are eating our primary consumers. So the hyena will eat some vegetation, but will also be a primary consumer. Lion is definitely a secondary consumer. Cheetah is strictly a secondary consumer, but then we also look at organisms that are scavengers. So scavengers means they'll eat dead things. So hyena he won't discriminate. He'll eat things that are alive and he'll eat things that are dead that he hasn't killed. The lion will do that. The vulture exclusively will only eat things that are dead. We have this little guy over here, this little vegetarian over here, this giraffe, and we have this acacia tree. if we look at this little category here, this is a detrivore. And a detrivore is an organism, such as the dung beetle here, that specializes in breaking down dead tissues and waste products, which detritus is the word for those things, into smaller particles. Those smaller particles can then be utilized by these decomposers here, which are going to recycle the nutrients from the dead tissues and waste back into the ecosystem. So scavengers, detrivores, and decomposers are really important to the food web because they recycle the organic matter and the energy back into the ecosystem. If not, we'd have these piles and piles of dead plants and animals. But the food web takes into account that it's much more complicated than that really simple food chain. And you need to have a good understanding of both of those for the APES test. Ecosystem productivity. The gross primary productivity, the GPP, is the total amount of solar energy that the producers in an ecosystem capture via photosynthesis over a given amount of time. It's a way for us to look, gross here indicates total, okay? It doesn't subtract the energy lost when those producers then respire. So the net primary productivity is the energy captured minus the energy respired by the producers. You can sort of think of it in terms of a paycheck. GPP is like the total amount you get paid, but the NPP is the actual amount you take home after taxes. So GPP is how much photosynthesis is occurring over some amount of time. And it's a challenge to figure out because plants don't often photosynthesize without also respiring. So it's hard to figure out. We can do some measurements to figure out the rate of photosynthesis. But we want to keep this idea that it's not 100%. Here's a little diagram to say, here's the sun. The sun gives us a tremendous amount of energy. 99% of that solar energy is reflected or passes through producers without being absorbed, not even part of it. 1% of that solar energy strikes the producers is captured in GPP. So 1% of what comes from the sun is captured. 60% of that is then lost to respiration. And then 40% of that supports growth and reproduction of those producers. And so we're down to 40, that net PP, that net primary productivity being 40% of the 1% that we actually harvest from the sun. We're looking at energy transfer and efficiency in trophic pyramids. So biomass is the energy in an ecosystem measured in terms of biomass. How much mass, total mass of all the living matter in a specific area. A standing crop is the amount of biomass present in an ecosystem at a particular time. So the amount of energy in a given time from the productivity, which measures the rate of energy production over a span of time. So slow-growing forests would have low productivity. The trees only add a small amount of biomass through growth and reproduction. But the standing crop of longleaf trees and the biomass of the trees is accumulated over hundreds of years is quite high. High growth rates of algae living in the ocean make them extremely productive. But because primary consumers eat these algae so rapidly, the standing crop of algae is relatively low. So there's two ways to sort of look at that. Ecological efficiency is the proportion of the consumed energy that can be passed on to one trophic level to another. And this is the idea I was speaking with earlier. This is that 10% rule. That's only 10% of that energy can be passed from one trophic level to another. And then the trophic pyramid is the representation of the distribution of biomass among trophic levels. So that was that sort of pyramid showing, we were looking at the bottom, producing a certain amount of joules of energy, moving our way up to our primary consumers, and then our secondary consumers.